Okay, we'll get started. Greetings, everyone. A very warm welcome to you all to this webinar hosted by the North Central Climate Adaptation Science Center, also called the North Central CAST, which is based at the University of Colorado Boulder. We are glad to be back online for our 2022 fall webinar series. I'm Imtiaz Rangwala, Climate Science Lead at the North Central CAST, co-hosting this webinar with my colleague, Heather Yoakum, who is our Stakeholder Engagement Lead. We bring you these webinars to facilitate a discussion of science, research, and best practices related to adaptation and resource management under a rapidly changing climate, with a focus on the North Central US that encompasses the Missouri and the Upper Colorado River Basins. Before I introduce our speaker, a quick word on housekeeping. We are recording this webinar, and you can find all our webinar recordings on our website. During the webinar, all participants will be muted, but you will have the ability to unmute during the Q&A period at the end. We, however, encourage you to put your questions and comments in the chat box anytime during the webinar, and we will start with those questions first during the Q&A in the order they are received. We will end the formal part of this webinar at noon Mountain Time and stop the recording at that point. After that, anyone who wishes to stay on to engage in a more informal conversation with our speaker is encouraged to do so. And now it is my absolute pleasure to introduce Dr. Bill Travis, who is our speaker today. Bill Travis is an associate professor in the Department of Geography at the University of Colorado Boulder. He's also the university director of the North Central CAST, the deputy director of Earth Lab, and a research affiliate with the Western Water Assessment, which is a NOAA RESA program. Bill's teaching and research focus on human behavior in the environment, including studies of human dimensions of climate change, land use, and the interaction of people and ecosystems. He began to study social response to climate variation and change in 1978, analyzing how wheat farmers adapted to drought and on the Great Plains. His current research projects focus on climate risk and decision analysis in agricultural, infrastructural, and ecological systems, with a focus on the role of extreme events in adaptation. He received his PhD in geography from Clark University. His talk today's title, The Challenge of Planning for Extremes in Natural and Cultural Resources. Thank you, Bill. Please take it away.
So am I unmuted?
Yes, we can hear you.
Okay, great. Hey, it's so good to be with you all. And here's my abstract and title. This may come across today in 40 minutes as something a little bit more like a class lecture, because I have to just admit, I've been teaching natural hazards, response to disasters, and more recently, forensics of disasters for all my career since 1980. And so I can't help but bring in some class-related material, and I just hope you'll bear with me on that. Let me get so that this is advancing. We'll do three. I want to look at extreme events in three ways, very briefly each. The theory and concept and analysis and how we define extremes. But then I think what you'll find more interesting is to draw on your own experience and the literature out there on how we study the impacts in our responses to extreme events and to cases. And this is a very case-rich part of disaster, extreme event, accident analysis, and some of which I think has some application. And I'll leave you, and hopefully you'll chime in at the end on how much application there might be to managing natural and heavily managed ecosystems. Because as you can imagine, a lot of the literature, a lot of the research comes out of industrial accidents, aircraft accidents, nuclear power plant accidents, And so that forensic part, let's just see what it tells us and maybe what it doesn't tell us. And then, of course, let's talk a little bit about the role of extremes in our adaptive responses. And I'll hopefully save time. There'll be time for you to share your experiences. And I understand that at noon, these webinars have also turned into another 30 minutes of more informal conversation. It seems to be, and my interest got piqued just recently again by events. I was scheduled to be camping right here in Pebble Creek in August in Yellowstone National Park, right there at that red circle. I was in that campsite a year ago when a heavy rain event came along and the creek rose. And my wife and I are sitting in our camper talking about, well, what would we do if this creek flooded? And we decided, well, of course, we would go over here to this part of the campground because we're not going to move the camper in time if there's a flash flood. The creek was high and muddy after a day of heavy rain. Well, a year later, the campground was destroyed by the Yellowstone floods. It just seemed like we were experiencing a lot of extremes, notable extremes. I'll just mention the flood and debris flows in Death Valley. Here's Brad Udall's picture of a former part of the reservoir of Glen Canyon. And also, some of you perhaps saw this. I was quite intrigued by the Chief of the Forest Service report on the prescribed burns in New Mexico that later this spring, winter and spring, that two of which became very significant wildfires. And we want to return to that report and learn a little bit about that kind of forensic analysis of events. Let's remember, think, conceptually, in a way, the extreme's not very well-defined class of natural or social conditions, kind of like we know it when we see it. Oh my goodness, Bill and Ann saw Pebble Creek rise a year ago. This year it rose and wiped out the campground. Okay, so this one was really the unusual event. But we do have we've all maybe taken the stats class, and we have a couple of ideas of how we might define extremes. In the extreme value theory, you could do it simply by, hey, give me a threshold above which you want to call the conditions notable, extreme, or somehow to be dealt with in a special way. The 90th percentile, I keep using that in various pieces of research, as I'll mention. And of course, then the challenge is choose the threshold, what really matters. The other way that we thought about it or been trained is it's a distribution of events in nature or society. They occur randomly over time at different magnitudes. And this, of course, requires us to define the event. And that's much more, that's worth paying some more attention to. What do we mean by the event? What is an extreme winter? What is an extreme rainfall event? What all goes into it? What are the compound parts of it? But of course, we learned in stats class this idea that you as you observe events, you were in a way you were drawing these. Well, you know the story. You're drawing these balls, the red or green balls, out of an urn. It has a certain number of red or green balls, and more interesting, and that's how you understand over time by recording the observations. What the distribution of those balls are. Maybe we ought to think about those balls as not just two colors, but they're all different sizes. And in the middle, there's a bunch of middle-sized ones, and then there's a few really small ones and a few really big ones. And if we were drawing them, what would we decide about that range of magnitudes? Now, the other, I just remember this from my inferential statistics class way back at Florida State University in the 1970s. If you had two bottles of different, with different relative number of, say, red and white balls, how many times would you have to reach in with a blindfold on and pull out a ball and get the red or white before you could decide which one you were putting your hand in, the A or the B? This brings up other approaches to inferential and Bayesian approaches, like what do you think the underlying distribution of events is that you're experiencing? And you can think about this statistically, but you can also think about it philosophically, or even from first principles, from your field of ecology or meteorology or physics. But we can't help but still be, most of what we'll see is that statistical thinking. What's that distribution of events? And we expect maybe nature often to show us a relatively normal distribution. Here's annual precip in Flagstaff. There's a wind speed histogram for some site. Honestly, I can't even tell you where. But look at that right tail of the wind speed distribution. Here's a few outliers, we might call them. And the word outliers is used lots of different ways, often without good definition, by the way. What are these events out here? And maybe more importantly, a big question for us is, how big, how long is that tail? How far does it stick out? So I have my students analyze a number of snow, almost 2,000 snow observations at the Boulder Airport. Number of days with snow and how deep the snow fell, how much snow fell during that day. And of course, there's lots of small events, and there's just a few. You actually can't see them, can you? There's actually a 24-inch, one 24-inch event in about 60 years. And I don't know. Is that the biggest that I lived here during that event. I remember it. Is that the biggest that we might experience? It certainly was disruptive. We'd call it extreme. But how far, what could nature do? What could the atmosphere deliver if it had everything it needed, all the moisture it needed, all the precipitation processes, the right temperature? How much snow could it deliver? Now, there's some limits here, and one of them is actually a social limit. These observations are calendar days. So whatever the atmosphere is going to do, it's got to do it in sometime between midnight and midnight. And a snowstorm might not be that way. So a lucky snowstorm starts at midnight, puts out an inch an hour. Next thing you know, there's 24 inches. But that same snowstorm, if it started at noon, would be 2 12-inch snowfalls. So the observations, and this is just an example of how observational bias can matter a lot to what we know about a distribution. Now, I ask my students to say, okay, what's a probable maximum event, or what's a 100-year event? You might think about it, you might put it in the chat. What would be your guesstimate for a 100-year snowfall in Boulder, looking at this histogram, knowing that in 60 years or so, we've seen a 24, we've seen the upper teens, and we get lots of small ones. What could we get? And if everything in the atmosphere were working just right to dump snow, the big dumps, what could it do? What could it do? But you got to keep in mind, there's physical limits, of course, on precipitation processes, and some of you would know those, some I don't. But there's also this social limit. It's got to do it within a daily, a calendar day. And that probably biases this data to smaller events, almost certainly, as I have the students pay attention to. Now, I asked them to do it a couple of different ways. Some of them are, there's engineering students in there, there's applied math students. So some of them do, as extra credit, do some extrapolations that really make some good sense. So let me show you what some of them saw. They tended to find the 100-year event to be around 27 inches or so, maybe as much as 29 inches, but somewhere between that big event that was observed and some extrapolation. Here's some other ways that students have done it. This student got a 100-year event of about 29 inches. Like an old-fashioned Corps of Engineers analysis. This student plotted it on log paper and also got about 28, 29 inches. And one thing I tell them is, look at the numbers, but also think intuitively. Even if you've only lived here a few years, you've got to have a sense as to how big this event could be. If all the conditions conspired to put as much snow down in a calendar day, I think that's probably, those are good numbers. I'd be interested to see when I get a chance to look at the chat what you were, if anyone put anything in the chat, what you were thinking. Now keep in mind that, thank goodness, we live in this universe in which big events are rarer than small events. In our multiverse, it works out that way. And the bigger events occur less frequently, which means on average, there's more time in between them. And this is really one of the great problems of natural hazards response and disaster response. What my advisor called the atrophy of time. In between events really big, if there's 50 years between two big hurricanes in New Orleans, a lot can happen that reduces our preparedness for the big event. We might even decide that it's not worth doing much to prepare for an event that has that relatively small return period. And we'll have to return to that. The standard approach is to take some set of observations, plot them, flatten them with a log transform, and then extrapolate to say, okay, what could happen at this place so that I know what the maximum gust would be over some period of time, or what my probability in any given year is, so I can say build a wind generating a wind generator that will stand the 99th percentile wind gust. And then after that, well, then I guess me and the insurance company will be picking up the pieces because I've designed it for a certain threshold, which brings us back to that common approach to assessing what extremes are. There's a new report out that came out after Katrina, in which the Corps of Engineers went back to its earlier storm surge analysis on the Gulf Coast. It's this remarkable report. This is actually from a draft of that report. And in this post-Katrina, this is the graphical fit of the curve of what a storm surge and this is good old-fashioned feet, 24 feet of storm surge above a mean high tide, I think, or a mean tide. And the idea after Katrina was to look back at what their plans were after Betsy. Betsy was a 1965 storm, and on this report, they actually went back and plotted what the engineering book said would be the likely return period of storm surges after Betsy. Now, one reason they bothered to do this analysis is that they decided after Betsy, here's some pictures of Betsy, they decided after Betsy to build an integrated protection system to keep storm surge out of most of New Orleans and the suburbs. And that was the beginning of a long story. And the analysis has this funny quality, is that the engineering team had this number here for Betsy, and they decided that after that event, we would imagine that we're kind of getting saturation, and the next biggest event would not grow as steeply as Betsy. Betsy was a very impressive event. Now later, 50 years later, they come along and they have a Camille and they have a Katrina, and you've just got to be surprised. Here you are looking at all these events, and you've got this, what you might have thought of at the time as a worst case, and you wait a little bit longer, and next two events are double what you thought of was a bad event. Not just 10% increase, not 20%, but they're double what you were thinking of as, in this case, what used to be called a standard project event. And this is really one of the boogaboos of extrapolating to events that we haven't observed or that we worry might occur. The idea that there are these long tails in those distributions, and out there we don't know, well, gee, what would the next biggest event be? Is it just a few more feet, or could it even be double, or could it be triple our historical observations or our instrumental observations? This was an issue as people responded for tsunami protection after the 2011 tsunami in Japan. Now, in the water resources field, the idea is that you can extrapolate to these big events, plus you design systems so that they can handle that, plus a safety buffer. Gene Stockey, one of the earlier hydrologists in the Corps, who was paying attention to climate change issues back in the 1970s and 80s, was very skeptical that climate change would be an important part of hydrologic planning in the near future, meaning through the early part of this century. But I think he came around and he published this paper, which I'd recommend to you, in 2011, suggesting that we were regularly underestimating what those bigger events could be. And he did it in a couple of ways. One, he took the statistical approach, suggesting that the standard distribution, the theoretical distribution that's being fit, like the generalized extreme value distribution, or traditional distributions that would be fit and used for extrapolating, we're probably underestimating significantly what events would occur, say, at the 100-year and 500-year return period, again, because of the difficulty of having, of learning, as the stats would do, learning what that distribution really is, and suggested that he didn't really suggest that we were always doing it wrong, nor that the solution was to do better statistics, because you could be wrong still, but to be very mindful of the value we were getting out of robust design, the value we were getting out of buffers, and why, say, Glen Canyon Dam didn't overtop in 1983. Or Oroville failed completely in 2017. The design of buffers, excess capacity, and he recommends more attention to that, of course, in a changing climate. I just want to drop back to this idea too, that I mentioned the difficulty is thinking about, well, what's the event like? And here's annual rainfall plotted for, I think, 50 years for Boulder. And it's got this quality, yeah, we know what our mean is, but this thing appears to actually have, like it's got two peaks, it's got two modes, it's bimodal. It looks like it's actually two distributions fitted on top of each other. And I think that's where we're learning more about this, that events, the way we define them, are not these singular discrete things. They're made up of different sets of processes. Like, for instance, just a guess, I'm not a climatologist, I'm just going to guess, maybe this drier distribution of our annual precip is La Nina years, right? And the weather distribution is El Nino years. But we don't think about this data as expressing two different populations. We think of it as one population, annual precip. And that can mislead us. That can mislead us on the probability, near-term, say, probability of a particularly wet or dry year. And also, the other problem, a challenge, is that the distributions may not be stable. I've just always been impressed by this lower graph, which is Sahelian rainfall up through the end of the last century. Partly this was being created by a group of climatologists who had to find the data. There's not a lot of data on Sahel rain gauges. And one of those climatologists, Sharon Nicholson, was on my committee, at my PhD committee, and I learned from her what they were observing by 1980 at my thesis defense in her work on African rainfall. And they were very surprised at what they were observing. Imagine that we were right here, 1981, right? And she was pulling together the best set of Sahelian rainfall records that you could get and publishing them, and seeing this switch that occurred around the middle of the previous century to a wetter episode, and then a swing to a remarkably consistent dry episode, which we were we didn't know that at the time. We were in the middle of in 1980. And this is still debated as to what was going on, why this occurred, whether there were local feedbacks through dust loading of the atmosphere that made this part of the globe move from most, you might say, a random distribution to something that had a very, a red signal in it, a long-term signal in it. And this is worrisome, of course, if you're trying to manage resources, water resources, and you're switching from one type to another type of regime. And that we'll find out in the forensics is a big issue. I want to say that it wasn't hazard managers, people who studied disasters, floods, earthquakes, hurricanes, always knew something that became a little bit more enthusiasm lately to write about, study what people are calling compound extremes or compound events. Now, anyone that was dealing with, say, Betsy at the time, understood that it was a compound event already. It had to do with the fresh water coming out of the Mississippi, whether or not the tide, the astronomical tide was high at landfall, what the bathymetry was. These are always, it's really hard to find an event in nature that you wouldn't think of. The minute you become more expert in that field, you wouldn't think of as a compound event. But we're hearing more about this notion that there's compound events and that they result in larger impacts. I think in reality, we've always been observing these events, but we're learning a little more about what pieces are, what these interactions are. A group of us in EarthLab wrote in Earth's Future a few years back an attempt to bring out conceptually how we might think about socio-environmental extremes as interacting events, not compound events, in which you have to recognize that the thing that you observe could come from some processes that actually dampened the outcome. I'll show one in a second. Or from processes that took maybe small perturbations and small events or small disturbances and made them into larger disturbances in the environmental or the natural system and in the social system. Here's one I think we still struggle with this here on the Front Range. We had this unbelievable rain event in 2013, and it looks like it's a very rare event. Every rare event is called a 1,000-year event, so it's hard to say what its return period are. These numbers, they're not quite meaningless, but it means it's really rare. If you see one of these in your lifetime, count yourself lucky or unlucky, and you probably won't see another one. Yet on the creeks in Boulder, this yielded more like a 50 to 75-year peak flow. And wow, and people were being flooded, not in the floodplain, just from overland flow from this heavy, large mesoscale rain event that we had that did set records. I got 17 inches at my house in 2.5 days. Our annual rainfall, right? And when we were writing this paper, Matt Rossi is a fluvial geomorphologist, and he included in the paper the literature that is finding that even as, say, parts of the U.S. have gotten wetter, especially after about 1993 in the Midwest and the North, other parts of gotten wetter on average, it's hard to see that in increased flooding or increased flood peaks. And why? Why is that? It makes so much sense. And of course, well, there's a variety of reasons. One thing is this heavy rain event was distributed over a few days. The history of flash flooding here on the Front Range is driven especially by convective events, two types of conditions. Really heavy thunderstorms that hang up over the foothills, like the Big Thompson flash flood in 1976, or rain on snow events. And speaking of that, and this was neither of those, right? And then that's what creates the peaks. This thing doesn't create peaks, but it creates volume, and that water was everywhere. Speaking of that, it's pretty clear, there's not a lot of publication yet out on it, that the floods in Yellowstone are one of these things, right? This is a rain on snow, but a rain on snow quite late in the season. So here's this snowtail is up just outside the northeast corner of the park, up at Beartooth Lake. And I went up there to get that because it still had snow on it. This black line is the 2022, and this is the snow water equivalent. And all the way to June, there was 20 inches of snow water equivalent sitting up there. And then here's the melt, and then it goes to nothing, a bare ground at the snowtail. Here's the max, here's the min, and let's make sure that we know the median is this green. So this year, this was above the median. There was some more snow late in the season. And then on top of that, at the same site, they measure precipitation. So we'll call this rainfall. And these two little bumps in the precipitation cumulative record are two rain events. And they rained hard, yes. There's at least been one set of meteorologists who study atmospheric rivers that say this was the eastern edge of an atmospheric river that came ashore over Oregon at that time. And that rain fell, and it brought warm air and heavy rain out through the atmospheric column. There were a lot of precipitation, warm precipitation processes, even at elevation, and that rain fell on snow, melted the snow. And if you got 5 inches of rain and 5 inches of snow, water equivalent to melt, then next thing you know, your catchment has a 10-inch event. And the results were catastrophic. I just was up there just a month ago, still in that northeast sector where the road is closed, and you could get a permit to go in to fish, and you can see some of the remarkable hydrologic work and geomorphic work that was done by that event. The other, thinking about those the concept, let's see, those contingent events makes us think that, well, okay, we ought to be convinced that almost anything that we're interested in, a really bad winter, a heavy wet summer that makes it hard for, say, ptarmigan to fledge their young or whatever, and excuse me, I'm not expert in that. These are not so easily discretable events. They're all compound events, and we may even be experiencing different populations of events. So when some colleagues and I looked at a really well improved wildfire occurrence record for the U.S., Virginia Iglesias, Jennifer Balch, and me, we made a point of trying to be open to, in looking at the numbers, the statistics, burned area and frequency in different parts of the country, and also over different time periods, because we were looking for some change over time. That's been discussed a lot in the literature. We wanted to see if we could find it, working hard on the statistics. The idea, we were really open to the idea that let's not just assume that fires are all just one population. And I think you can see that in some of these graphs in burned area and fires per week. And there's a couple of lessons, and I won't go over them right now, but they're in the paper and in our blog about the paper. And one is that when there's lots of fires, there's also a tendency for there to be some big fires. The record big fires occur in periods of time, and these are weekly analysis, in periods of time when there's lots of fires. Okay, fine. And we also, by the way, since there's lots of fires in these periods, the fires are closer together geographically. I mean, that's inevitable. It's a truism, right, of the geography of that. But it may well be that those years and or those types of fire situations are a separate population that has a different process behind them, like a very large out of season set of lightning storms that create a bunch of fires and then they merge into the big ones. I think that you can see that there are these other distributions, these other populations out at the bigger end. And just looking at that, now fire behavior analysts and others, burn bosses and all, they know this, right? Because they see these events, and they know that a combination of vegetation and condition and climate and wind and ignitions can create very difficult conditions, including maybe a whole population of mega fires. We also tried to get the same, looking at the underlying climate conditions for essentially drought, looking at drought. And we used the approach of defining a threshold that we cared about, the 90th percentile. And we found differences. A typical drought forming in much of the U.S. has not changed much over time, but the fastest developing droughts, which are becoming known, people are calling them flash droughts, are speeding up. Those top 10, or in the top 10, the top 10% of events are becoming faster, and they're responding more than the median drought. They're responding to some driving force, which would, I think, have to do with, as Imtiaz would tell us, faster depletion of soil moisture in warmer droughts that are not just precipitation deficits, but are warm precipitation deficits. The other idea of compound events is that how do you know what's coming? I'm just struck by Jennifer et al., Balch et al.'s work on how nighttime conditions have especially, the more recent Holocene, have been a quieting force on wildfire, as many fire experts know, firefighters, that things lie down at night. And warmer nights then allow more active fire at night. And if this is occurring, then you might start to see those bigger events, maybe more frequent, but more frequent big events. And you could imagine, okay, there's vegetation changes over decades and centuries. There's maybe a hint of a climate change in nighttime temperature or nighttime vapor pressure deficit. And these sorts of combinations of processes, getting the dry spells that are also hotter than they were in the past, or warmer nights or nights that allow more extreme fire behavior, are yielding those bigger events. Now, some of these processes are, I would assume, creating some, dampening some events. Remember our graph. Some of these processes are bound to be negative feedbacks on magnitude. But of course, we're especially interested in trying to tease out what we face in a warming world in terms of the positive feedbacks. I'd recommend, if you get more interested in how extremes change with climate change, obviously the big question that's discussed in almost every New York Times article about extremes. There's this wonderful article that we should all be reading by Tom Wigley. He wrote it in about, I think, 1988 in an in-house journal called the Climate Monitor, the Climate Research University of East Anglia. And thank goodness that Climatic Change republished it in 2009. And he showed mathematically, before we had seen these pictograms of how changing distributions might affect the tails, he showed mathematically how, because of the nature of basically the curve of the distribution, that as you shift them, you may find per unit of shifting, you get a amplification per unit of extreme event or magnitude. And that was a really neat article at the time. I remember reading it and thinking, wow, okay, we need to be careful, because if we're paying attention to the means, and that was his point, right? If we're paying attention to the means, we may be surprised at what happens in the tails. And I think that, we certainly found this. One of the moments that we're in is that we now have decades of anthropogenic warming that's actually affected the environment around us, and many of us are observant enough to see it. That wasn't true when he wrote this as much in the 80s. When I started working on the questions of the impacts of climate change, we were always thinking, by 2030, there'll be hotter heat waves, maybe longer droughts, and I don't remember even reading about the potential for increased precipitation intensity, but it was all, 50 years away. And now we've got 50 years under our belt, which I think helps us grapple more with events. Let me talk about events, and I'll wrap up with this. I decided that I wanted to start to build to take a more forensic approach to extremes, and I would ask you if you'd like to contribute. So I asked my students in a few hazards class to go find an event that had some forensic study behind it. That, in most big events, someone ends up like the Civil Aeronautics Board or someone in FAA ends up doing a report, what went wrong. And so we started building this database of natural and technological disasters, and try and pull together the reports of, okay, what led to this event. Now, this is not new, by the way. People have been doing this. Psychologists, sociologists, engineers, and others have been trying to understand what are the general lessons from extremes, and we took the, if you will, the theory out of these thinkers on extremes, and we're coding these events by what sort of theoretical process seemed to be going on that led to, say, the Deepwater Horizon explosion, the failure of the Teton Dam, and other cases. And what I lack in here, and of course, I've been impressed over my career by particular events. I was told to study this when I was a graduate student. My goodness, the Challenger accident in which a loss of a vehicle and crew. And it has, of course, one of those forensic studies, a very famous forensic study, because one of the members of the team studying it was a physicist, Richard Feynman, very smart physicist, Richard Feynman, who has other human flaws that history has shown. But he was really important to the study by questioning the safety that was assumed by NASA and others on the space shuttle. And it's really worth reading his report, his minority report, Appendix H in the Presidential Commission report on the Challenger. Even today, it's worth reading, because he started getting tips from NASA engineers and others, and there were kind of like two camps, almost like two populations. And one camp was that the system was made to be really safe, really, really, really safe. We've done everything we can to make it safe. And we've got the probability of a catastrophic loss way, way, way down. Maybe as few as 1 in 10,000 or 1 in 100,000 flights. Now, a lot can go on, but catastrophic loss is down there. But he then heard from, say, in what he called the working engineers, that their sense was, no, we know this system, it's pretty unruly, it's new, we keep running into small problems that make us a little nervous that there could be bigger problems, that thought that potential accident rate was much higher than those first pre-shuttle estimates, by the way. And that reliability is somewhere more like 1 in 100. Guess what? The flight, the program, which is now ended, actually did have 2 loss of crew and vehicle accidents in flights number 25 and 113 out of 130 flights or so. And that's 1 in 65. The actual frequency of those catastrophic losses was more like what those engineers were telling Feynman and what he thought than those really remarkably risk-free estimates. And you have to wonder how much we're underestimating the tendency of complex systems, especially new systems like the space shuttle, or even that system they built to protect New Orleans after Betsy. How likely are they to fail? There's a big question. How likely is some plan we're putting in place likely not to go the way that we want it to? And I'll just briefly mention some of the studies that we've got in our database. Of course, Katrina, what went wrong, what the responses were. This was a very honest set of assessments. With still some, if you will, Cassandras. I think I got my mythology right. Cassandra's telling us that, hey, you've been in here trying to fix this system. Thank you for all those new flood walls and all. But is it really fixed? How secure should we be in future hurricanes? These are some of the same authors that question the original system. One might learn some lessons about this from the study of Fukushima. A seawall or common seawalls along for tsunami along that northeast coast of Japan. It's a very tsunami-prone setting. I remember in my textbook I use in a hazards class, there's a damaging tsunami every decade somewhere on that northeast coast of Japan. It's quite remarkably. And it's had big tsunamis in the past, but for some reason, which has been studied in a set of researchers of the Society for Risk Analysis, for some reason, the tendency up and down the coast was to plan for about an 18-foot tsunami, and that came from that analysis, right? Those 18 to 20-foot tsunami walls were completely overwhelmed by something more like a 30 to 40-foot tsunami in 2011. This picture here is really tells the story. This is the new concrete tsunami wall up south of Sendai, and it's built onto the old tsunami wall, which you can see the old concrete right here. So this is a reflection not only of how big the next event was compared to what the historical record suggested, but also how the humans have decided to respond, which is to try to build a big enough protection system, because there's too much invested in these towns to abandon them, a big enough protection system to handle what might now be thought of as the probable maximum event. And we think about all our systems. They have different sensitivities, different vulnerabilities, and some recent cases keep reminding us of the energy infrastructure in Texas in 2021, the very close call at Oroville Dam in 2017, when the spillway had to be used because of a rapid fill of the reservoir. There's something special about this story. This is after about 5 years of drought. And so all the rain and snow that was coming into the reservoir was so appreciated to fill that reservoir. And the reservoir managers did not violate their flood control rules. But the next event in late January and in early February put so much water in that they had to use a full capacity of the spillway. And it hadn't been run since the 1960s when Oroville was built. And it physically failed. That meant that they had to cut off water going across, and the reservoir began to rise further and started to spill over the emergency spillway, which wasn't ready to handle it yet. Here's that.
Just a quick time check, Bill.
Yeah.
Okay.
Oh, and tell me my time. I should quit.
Yeah, if you could maybe make like one last point and then open it up for Q&A, that would be
okay.
great.
So systems can be really vulnerable. Natural systems, human systems can be really vulnerable. Obviously, to think about extremes, we have to look at both sides. We have to look at the extremity of expected events and the sensitivity of the system. You know, the 2-inch or 3-inch snowstorm that paralyzes Atlanta. The recent flooding on I-10 at the Arizona border, and we ought to think about a series of we can apply a forensic list to them of what were the precursors, what did we know about, did we see some close calls, some past events, what's a chain of events that could lead to the bad outcome, where might we find the weaknesses in our planning. And how might we find weaknesses in our response? And so I'm going to leave you with a couple of thoughts. And going back to that case set of cases we're building, it doesn't have much ecology in it, and I'd love to get more ecology. And I'm really excited by these times that we're in which, groups here at the Cask and others are using better tools than we've had in the past, better insights to bringing uncertainty and extremes into, say, species assessments, plans for resource management into the future. And it's just really an exciting time. I just mentioned, for instance, the study of mountain goats and how so many places in the analysis that just came out, just was published this week, right, brought in was formal assessment of uncertainty and the probability of conditions that would yield an outcome that the planners wouldn't want. Say in moving members across locations and moving disease with them, things like that. The uncertainty that MTOs and others have been writing about that links the uncertainty of climate with the uncertainty and complexity of ecosystems. And the potential for tools, planning tools that are up to snuff in dealing with uncertainty, extremes, and of course change in Earth systems. And I'll mention a paper that Brian and Mitch and others have, Gregor and MTIs have in review right now that brings together some of the tools that we've used traditionally, scenario planning and structured decision making, into a scenario-based decision analysis, which can be really much more sensitive to learning, adaptive management, as well as learning from extremes. And I'll end with that, because just to say that I believe that we're making some progress in the ways that we can bring uncertainty and extreme events into at least our assessment. And it'll have to just be another webinar to talk about how we should adapt to these events. I'll leave it to that. Thank you.
Thank you so much, Bill. I'm going to give you a little round of applause right here before I open it up for Q&A. So I don't see any questions in the chat right now, so I'm going to make it so everyone can unmute themselves. If you have questions that you would like to pose to Bill, give me one moment, and then you can unmute yourself and ask that question to him directly. But maybe I will just take some organizer privilege here and ask maybe the first one to get us started. And Bill, I want to say, I really love the point that you made about kind of observational bias, talking about like, is it 2 days of 12-inch snow, or is it one 24-hour period with 24 inches, and kind of where you move towards the end of your presentation and thinking about really the impacts and how maybe like several moderate events that come in quick succession can be worse even from an impact perspective than an event that maybe fell really into those tails. So I was just wondering if you could say maybe a little bit more about that, about how we as society experience those impacts and how that figures into the thinking about how to define extremes, particularly when we're thinking about climate adaptation.
And well, let me start by saying I think there's a certain pathology in our scenario approaches. Here's what you might do in a team. You might ask a few members of a team to be the red team, right? To do worst case analysis. And that can be really valuable. They can spend some time thinking about, okay, well, what would happen if 3 of these occurred in a row, or 2 Marias hit Puerto Rico for the wildlife refuge there in the same season. And this does happen. It's 2004 in Florida, for instance. But sometimes those worst case scenarios just make the rest of the team say, oh, well, what are we going to do? Because they are so extreme. And there's a little bit of a pathology in that not being able to make use of that kind of those risk registers, as they're called in the business world. But in that risk literature, you'll find one of the ways that people have built scenarios, and in some of that, for instance, that study for mountain goats, built estimates of a likely failure or a problem like a spread of disease and what it would mean for the outcome of the plan, by not necessarily going to the worst case, but trying to find something that's in between, the best and the outcome that we would rather not have. You might be assigned, I see Jeff Lucas is here, you might be assigned with getting at the probable maximum event, or the biggest failure, or the biggest set of events that would really put you in trouble. But more likely, of course, is a set of just more moderate events that compound and cause some part of your effort to fail or cost you more money. And I think maybe sometimes when we go to the worst cases and we come back to our team and say, here's some of the worst cases, everyone gets sticker shock. Because to be ready for the worst case, it's just we don't have the time, we don't have the money. Well, maybe if you're on the northeast coast of Japan and you're building those 35-foot concrete walls, you should Google this and look at the pictures of what they're building up there. Yes, you can do that, and the Dutch did it, and others. But in most of our plans, we're going to have to find some way to reduce our vulnerabilities, I think somewhere in this middle ground, and more get a credible assessment of what could go wrong. And there's something also a little bit magic in some sensitivity analysis, or what risk assessors call a risk register, is that once you start to pay attention that what could hold up your project, what could cause it to turn out less well, you might actually find that you're not that sensitive to some events, that you're not that vulnerable, and you'll be able to decide to take off the table a set of risk and then focus on some other. So often sensitivity analysis and other approaches like that in scenario and in structured decision making actually let you let you worry a little less about some populations of events and bring your attention to mitigating elsewhere.
Great, thank you. I will open it up to you folk. You should have the ability to unmute yourself. If you can't, either raise your hand or say something in the chat, and I'll try to unmute you individually. Yeah, Mindy, go ahead.
I have a question. If you think these extreme events are causing ecosystems to become less resilient, there was a paper that came out in the last week or two, and I was just looking at it. It's about some at the Stockholm group or whatever it was, basically saying that the world's ecosystems are becoming less resilient. Do you think these extreme events are causing that to happen?
Yeah, so this is really outside of my expertise. So thanks, but I think maybe that's where you're going, Mindy. But if I get the field of ecology right, especially simplifying ecosystems, and so maybe the big question is, do the big events, the big winters? I remember 1982, 83 here in the Rockies. I remember walking into the BLM office in Rollins in January, and there were two pronghorn sitting on the sidewalk, and they couldn't even move to let me go by them. They were basically dying from that extremely cold El Nino snowy winter when some large proportion of the pronghorn population in Wyoming perished. It certainly changed the population of the event, right? Does it then? What's the population dynamics after that? Are they more variable? Or so? Excuse me, Mindy, for not having much insight on that question.
I mean, I just think about with grazing. I mean, I'm just looking at the simple activity of annual grazing, in ecosystems. It so much depends on the recovery process. So ecosystems, like when bison came through the prairie and they just hammered it, but then they didn't come back to that ecosystem, that site for a couple of years. And so these longer periods of recovery allowed it to be more resilient in the long run.
Yeah, and the handbook for grazing in the short grass is hit it and then rest.
Right.
But I believe that. Well, I wish I knew more about it. But I believe that it's hard to know how much rest to give, and maybe hard for someone pressed up against the cattle market to provide that rest. But I'll just make that comment and then be quiet about it.
Well, and I will, oh, sorry, Mindy, go ahead.
No, I just was saying thanks.
Oh yeah, thank you so much. Excellent question. And I think I found the study you were referring to and I put it in the chat. So you might want to double check that that's the one you were referencing, but if folks are interested, I tried to put a link there. I will say we are about at time, so I want to give everyone an opportunity to jump off if you have to go about the rest of your day. I think that Bill has agreed to stay on for about another half an hour or so to answer any other questions if folks have some other questions, or if you want to just kind of continue the conversation, you're welcome. But this is your off ramp if you need one. So thank you very much for joining us today, and I'll stop the recording and we can keep the conversation going.